This is the video for Atwood machines. So the first one we are going to look at is where we have two masses hanging off the edge of a table, and they are connected by a single string. Okay? So, of course, our first step is going to be to draw free body diagrams for each. So we have one mass that is 2m and the other mass that is m. Okay, so the 2m mass has a force of gravity acting on it and an upward tension force. And the m mass has a force of gravity acting on it and a tension force. Okay. Now, even though these are slung over a table, there's no mass in the center, so there's not going to be any friction. Okay. So this is kind of just a larger version of an Atwood machine that looks like this. So there's not any difference between this and the table setup. Okay. It is the same string connecting the two masses, so we know that this tension here and this tension here are equal. Okay. To make our lives easier, we want everything to be moving in the same direction, because as it's drawn right now, this 2m mass is going to move down, this m mass is going to move up. That gets a little bit complicated. So we're going to stretch out our masses so they look like this. So we're just going to rotate our free body diagrams a little bit so they look like this. Tension, FGM. Now everything is moving in the same direction. Specifically, everything is moving to the left. Okay. So once we have that done, we're going to go ahead and draw our net force equations. Okay, and I'm writing in 2m because that is the mass of this object. So I have the force of gravity acting on that 2m minus the tension is 2ma. And then for the mass m, that's just going to equal ma. I have a tension minus FGM is max. So you may have noticed that I called the leftward direction positive. Again, I like to call the direction of motion positive just because it makes sense in my head. If it makes more sense in your head to say everything to the right is positive, that is fine. You'll still get the same answer. So we know that this tension here and this tension here is the same because we're connected, and we know that this acceleration and this acceleration are the same, again, because we are connected. Okay. So as we've done in many other problems, we can rearrange one of our equations for tension. This Fg is really the same thing as mg, and then we can take that tension equation and substitute it in. So this Fg2m is really 2mg, substituting in with parentheses, equals 2ma, distributing that subtraction sign, 2mg minus ma minus mg is 2ma. We got to add all the a's to one side. So 2mg minus mg. So this is 2ma plus a 1ma, so that gives me 3ma. And I do the subtraction over here, 2mg minus 1mg just leaves me with mg. It's 3ma. I have an m on both sides. Okay, so my acceleration ends up being g divided by 3. Okay. Or if I kept the masses in there, it would tell me that my net force is the difference between the forces of gravity, that's what I have here, over the total mass. Okay. So let's make this a little bit more interesting, and let's say that we now have a mass 2m on the table, and we need to figure out what mu s is so that the whole system is at rest. Okay. Remember, if we are at rest, our acceleration is 0, and therefore our net force is 0. So we have to draw some free body diagrams. Okay. the masses that are hanging down do not change. We still have just the force of gravity and tension. But the thing is we now have two distinct strings, okay? So that means we now have two tensions. So instead of just calling it T, I got to call it T1 and T2. Okay, so those are my hanging masses. Then I have the mass in the center, which is going to have a T2 and a T1. And if anything, this mass, this 2m mass on the table, it is likely going to move to the left. So that means my static force of friction needs to point to the right. And then in that y direction, we have an Fg2m and a normal force. Okay. So again, my whole goal here is to figure out the static coefficient of friction, which is hidden inside this force of friction. So in order to kind of simplify my problem, I want to take everything and make it move horizontally. So I can redraw my system as looking like this, okay, which then makes my free body diagrams rotate, where this is T1, this is Fg2m, okay, I have an FGM, I have a T2, and then acting on the center mass, I have T1, T2, static force of friction. I have an Fg2m and a normal force. Okay. So then I'd write out free body diagram, or sorry, not free body diagrams, net force equations for each of those masses. So for the 2m, let's call this A. So for mass A, I have the net force in the x direction. Now my whole system needs to be at rest, so this has to equal 0. Okay, so I have Fg2m minus tension. So I'm calling left positive because if the system is going to move, it is going to move to the left. Okay, because that 2m mass is larger than the other mass. Okay, so that's for mass A. So this tells me that Fg2m is the same thing as T1. So 2mg is T1. Okay, that's exciting. Then let's call this mass C. Okay, so the net force acting on that, again, the whole system's at rest, so we're going to have a 0. So if T2 minus the force of gravity acting on that mass has to equal 0. So this tells me that T2 is the force of gravity acting on that mass, which is just going to be mg. So those are my two hanging masses all set. Then I have that center mass. So let's go ahead and figure out the y direction for the center mass first. Okay, so I have a normal force minus an Fg2m. So my normal force is Fg2m or 2mg. The reason why that's important is because we do have a force of friction, so I will need to know the normal force acting on that center mass. Okay. So then in the x direction, again, equals 0 because we're at rest. So we have T1 minus T2 minus the force of static friction is 0. Okay. So I'm looking for the coefficient of static friction, so I'm going to move the force of static friction over. This is T1 minus T2. That's the coefficient of friction times the normal force. Okay. Remember that this T1 and this T1 are the same, so I can substitute in the equation for T1, which was 2mg. And then remember that this T2 and this T2 are the same, so I can substitute in that equation for T2, or the mg. Us, the normal force I already found was 2mg, so 2mg. Okay, so I have mg minus a 1mg, or 2mg minus a 1mg, which is mg. Us 2mg. Again, my end goal is to solve for us. I'm going to divide both sides by 2mg. 2mg. Okay. So mg ends up canceling. Remember, there's an invisible 1 up there, so it's not a 0 in the numerator. It's a 1. So that gives me a static coefficient of friction of 1/2. Okay. Now it makes sense that both the m and the g cancel because coefficients of friction are unitless. So there shouldn't be any units left over. There should just be numbers, which is true if we're left with a 1/2. So the coefficient of static friction between the table and that center mass has to be 0.5 in order for the system to remain at rest. Okay. All right. The last type of problem we're going to go over. There it is. Okay. So let's say we have a system with two masses. One of the masses is on an incline, the other is hanging over the edge. Our goal is to figure out what the mass of the mass on the incline should be if we are moving at a constant velocity down the ramp. And we're told that there's a coefficient of kinetic friction between the ramp and that mass. As always, we need to draw some free body diagrams. Okay, so for the hanging mass, we have an FGM and a tension, and this FGM is just going to be the same thing as mg. Okay, acting on the mass on the incline, we have a tension. Okay, it says we're going down the ramp, so that means the the force of friction needs to be acting up the ramp. We have a force of gravity, and we have a normal force. Okay, remember that anytime we are on an incline, FG is not in one of our coordinate directions. So we have to break FG up into components. And we do so based on this angle and here with vertical. So remember, FGX ends up being FG sine theta because that X component of FG is opposite of the angle. And FGY ends up being FG cosine theta because the Y component is the adjacent side of the triangle to the angle. Okay, so redrawing that free body diagram with those components, okay, we have a normal force, and that's always going to be opposite of FGY. And then we have tension, force of kinetic friction, and FGX. Now again, we see that we have objects moving in two different directions. One's moving down the incline and one's moving up. Okay, so we want to rotate our system or kind of spread out our system so that everything is moving horizontally. Okay, and everything is moving that way. So with that, we have to rotate our free body diagrams. So for my mass on the incline, we now look like FGY in the Y direction. Normal force. We have FGX, and we have tension and a friction force in the X direction. And then on mass M, we have tension and we have the force of gravity acting on mass M, which remember is just mg. I'm making a review video for my children. Mr. Andrus just stopped by, friends. Okay, so we have our free body diagrams all rotated. Everything is now moving in the same direction to the left. So now we need our net force equations. So we need a net force equation in the Y direction for this unknown mass. Okay, so it's a normal force minus an FGY equals 0 because we're at rest. So my normal force equals FGY. Now I don't know the mass, so when it comes to actually writing out like mg, I'm just going to call it xg cosine theta since I'm looking for what that mass needs to be. So if you see the letter x in my equations, that is what we're solving for, the unknown mass. I don't want to call it m because I already have an m in my system. Okay. Then we can do net force equations in the x direction. And because I'm moving, if you remember, at a constant velocity, my net force is going to equal 0. So I have an FGX minus a tension minus a force of kinetic friction equals 0. So FGX is the same thing as FG cosine theta minus tension. The force of friction is the coefficient of friction times the normal force. Okay, so this is xg cosine theta minus t minus mu k. The normal force is what I just found up here. So I can write that as xg cos, or this should be fg sine theta. Whoops, as fg sine points down the incline. There we go, and this is cosine theta equals 0. So it looks like the only thing stopping me from finding x, which is that unknown mass, is the tension. So I'm going to come over here and look at my hanging mass and apply a net force equation to the hanging mass. So the net force of the hanging mass is the tension minus the weight of that hanging mass. Okay, because we are moving at a constant velocity, my net force is 0, so those two have to equal each other. Remember, we can have a net force of 0 when we're moving at a constant velocity or when we're at rest. So what likely happened in this scenario is a big push was given to this unknown mass down the incline, and the system just continued to move at a constant velocity. So if my tension is mg, I can take that and plug it into this equation for tension because it's the same string. Okay, so I can know that the tensions are the same. So I have xg sine theta because mg sine points down the incline, or in this case, xg sine points down the incline. So minus mg minus mu k, xg cosine theta is 0. I'm looking for x, so I want to isolate x. So I'm going to add mg to both sides. So the xg sine theta minus mu k, xg cosine theta is mg. Okay, I'm again looking for x, so I want to factor out an x. So g sine theta minus mu k, g cosine theta is mg. So I'm going to divide both sides by that whole entire thing in the parentheses. So I get mg over g sine theta minus mu k g cosine theta. And if I want to simplify it, I see that there's a g in every single term. So I can cancel out that g, which leaves me with m over sine theta minus mu cosine theta. Okay. Now, it's not a pretty equation, but that is the answer, and it makes sense because the units of x, if it's a mass, should be kilograms. So this mass up here has units of kilograms. Sine is unitless. Mu is unitless. Cosine is unitless. So I'm dividing a kilogram by 1, essentially, which means my units for this side of the equation are kilograms. So that means I do have a correct and physically valid equation. Okay. So just as a reminder, our general process for these equations, or for these questions rather, is to draw a free body diagram. Okay. If we're on an incline or we have a force at an angle, you want to make sure that you're finding components. If we're on an incline, the x component is sine because FG sine points down the incline. The y component is cosine. So we take our free body diagrams and then we say, let's make everything move in the same direction. So we spread out our problem or stretch out our problem. In this case, I made everything move horizontally. So I rotated both of my free body diagrams so that everything was moving horizontally. Make sure that your tensions are equal in magnitude but in opposite directions. That's how you know you've drawn your free body diagram correctly. Okay, I said that moving to the left was positive since that's the direction my system was moving. And then from there, I wrote out net force equations for the y direction and x direction for the unknown mass and for the mass itself. I used those free body or those net force equations to solve and substitute in for that unknown mass x. And then I just